Hi everyone. In this video, we are going to see an important theorem in matrix algebra. Before coming to the main theorem, let us see few concepts which are required for the development of the theorem. First definition, what is a linear transformation? If V is a vector space over a field F, then a mapping T from V to V is called a linear transformation on V if T of x plus y equal to T of x plus T of y and T of Ax is equal to A into T of x for all the vectors x comma y belongs to V and for all the scalar A belongs to F. So if these two conditions are satisfied by the mapping T from a vector space V into itself, then we say that the mapping T is a linear transformation. The set of all linear transformations of V is denoted by home VV. So what is home VV? It denotes the set of all linear transformations of V. For convenience of notation, we shall write home VV as A of V because we can prove that A of V is an algebra over the field F. Hence, we can denote home VV as A of V hereafter. Coming to matrix of a linear transformation definition. Let T belongs to A of V and let V1, V2, etc. Vn be a fixed basis of V. Since T maps V into V, V1T, V2T, etc. Vnt, the images of the basis elements must all be in V because basically as T is a linear transformation, you all know T is a mapping from V to V. So the image is also elements of V. Since each VIT is expressible as a linear combination of the basis elements, there exist elements Aij of F uniquely determined by T such that V1T is written as a linear combination of n vectors as A11 V1 plus A12 V2 etc. A1n Vn. Similarly, V2T is written as A21 V1 plus A22 V2 etc. A2n Vn etc. Vnt is written as An1 V1 plus An2 V2 etc. plus Ann Vn. Why we are writing each VIT as a linear combination of the basis elements? Because each VIT falls in V and V1, V2 etc. Vn is a basis of V. So by the first condition of the basis elements span V. Therefore, each VIT is written as a linear combination of the basis elements. So these n equations for V1T, V2T, etc., Vnt as a linear combination of the basis elements. Of course, the scalars are taken from field F. These equations can be written in the condensed form as VIT is equal to sigma over j varies from 1 to n, Aij Vj for all I varies from 1 to n. So all those n equations are written in the condensed form like this. VIT equal to sigma over j Aij Vj. What are the scalars here? Aij for all I comma j varying from 1 to n. Aij's are the scalars taken from the field F. It is convenient to write these n square elements Aij. How many scalars are here? See how many equations here? N equations. Yes. So you are having n rows and n columns. So how many scalars are here? From A11 to Ann. In each row you are having n scalars. So how many rows you are having? N rows. So how many scalars are here? N into n square scalars. So it is convenient to write these n square scalars Aij in a square array as below. That is A11, A12, etc. A1n. First row scalars. Second row scalars A21, A22, etc. A2n, etc. Similarly, the nth row scalars an1, an2, etc. ann. So these scalars are put in the square array form like this. Such an array is called a matrix of the linear transformation T relative to the basis V1, V2, etc. Vn. You know, matrix is nothing but a rectangular arrangement of elements. So this array is called, is relevant to which linear transformation T. So this array is called the matrix of the linear transformation T relative to which basis V1, V2, etc. Vn. And it is denoted by, this matrix of the transformation T is denoted by M of T. Or simply you can write as in the name of scalars as matrix Aij. Before coming to the main theorem on matrix algebra, you should remember this theorem. That is the mapping T to M of T. That is every linear transformation, there is a one-to-one correspondence between a linear transformation and its matrix. So this T to M of T, this mapping is an isomorphism of A of V onto Fn as algebras. So this theorem we are going to apply in the main theorem we are going to see in matrix algebra. So statement of the theorem is, let V be a vector space of dimension n over F and let T belongs to A of V. If M1 of T and M2 of T are the matrices of T relative to two bases V1, V2, etc. Vn and W1, W2, etc. Wn of V respectively, show that there is an invertible matrix C in Fn such that M2 of T equal to C M1 of T C inverse. Coming to the proof, let M1 of T equal to Aij and let M2 of T equal to matrix Bij. Then from the definition of matrix of linear transformation, Vit equal to sigma over j Aij Vj and Wit equal to sigma over j Bij Wj. Let S from V to V be defined by Vis is equal to Wi for all I varying from 1 to n. Then it can be easily proved that S is a linear transformation on V. Now to prove S is on 2. Let Y be any element of V, then Y equal to C1 W1 plus C2 W2 etc. plus Cn Wn for all scalars Ci belongs to F, since W1 W2 etc. Wn is a basis of V. Using these scalars Ci, we find that X is equal to C1 V1 plus C2 V2 etc. Cn Vn, which is an element of V. We can express X like this, since V1 V2 etc. Vn is also a basis of V. Now consider Xs, that is equal to, substituting for X, it is C1 V1 plus C2 V2 etc. Cn Vn into S. Since S is linear transformation, applying both the properties of linear transformation, we get Xs is equal to C1 into V1s plus C2 into V2s etc. plus Cn into Vns. But since Vis equal to Wi for each I varying from 1 to n, now we get Xs is equal to C1 W1 plus C2 W2 etc. Cn Wn. But that is equal to Y. So we get Xs is equal to Y. So for every Y belongs to V, we have located one X belongs to V such that Xs is equal to Y. Therefore S is on 2. Since S is a linear transformation of V onto V, now S is invertible by a theorem which states T belongs to A of V is invertible if and only if T maps V onto V. So now S is invertible in A of V. Since S is invertible, we know S inverse exists. Now consider Wit. So by definition, it is sigma over j Bij Wj. But since Vis equal to Wi, we get Vis of T equal to sigma over j Bij into Vjs, which implies Vi of St equal to sigma over j Vij Vj into S. Since S is invertible, we get Vi St S inverse equal to sigma over j Vij Vj, which implies Vi of St S inverse is equal to sigma over j Vij Vj. Therefore, by the definition of the matrix of linear transformation relative to a basis, we get M1 of St S inverse is equal to the matrix Bij, but we know that is M2 of T. Since the mapping T to M1 of T is an isomorphism of A of V onto Fn, since we know A of V is isomorphic to Fn as algebra, from the above equation, we get M1 of S, M1 of T, M1 of S inverse is equal to M2 of T. So M1 of S inverse is nothing but M1 of S the whole inverse. So taking M1 of S equal to C, which is an element of Fn, we get the above equation as C M1 of T C inverse is equal to M2 of T, where C is invertible. This matrix C equal to M1 of S is called the matrix of the change of basis. So applying this theorem, we can see two problems. If T is a linear transformation on R power 3 defined by T of A1, A2, A3 is equal to A1 plus A2 plus A3 minus A1 minus A2 minus 4A3, 2A1 minus A3, find the matrix of T relative to the basis V1, V2, V3. This is the question. So T is defined. We are going to find what is M of T. Coming to the solution, from the definition of T, we have T of V1 equal to, substituting for V1, it is T of 1, 1, 1. So using the definition of T, it is, we are getting T of V1 as 3 minus 6, 1. Let x, y, z belongs to R be such that this T of V1 equal to xv1 plus yv2 plus zv3. That is, we are assuming T of V1 as a linear combination of V1, V2, V3. So now what is our task? We have to find what is x, what is y, what is z. So substituting for V1, V2, V3, we get 3 minus 6, 1 as x plus z, x plus y, x plus y plus z. So from this we get x plus z is equal to 3, x plus y is equal to minus 6 and x plus y plus z is equal to 1. So we have three equations to solve for three unknowns x, y, z. So solving for x, y, z, we get z is 7, x is minus 4 and y is minus 2. Therefore, T of V1 equal to our 3 minus 6, 1 equal to xv1 plus yv2 plus zv3. That is what we have assumed. Substituting for what we have found for x, y and z, we get T of V1 as minus 4v1 minus 2v2 plus 7v3. Let this be equation A. So these scalars minus 4 minus 2 S7 gives the first row of M of T. Similarly, going with V2, we get T of V2 is, substituting for V2 it is T of 0, 1, 1. That is equal to, using the definition of T, we get T of V2 as 2, minus 5, minus 1. As before, let us assume x, y, z be the scalars in R such that 2 minus 5 minus 1 is expressed as a linear combination of V1, V2, V3 as xv1 plus yv2 plus zv3. Substituting for V1, V2, V3 and after simplification, we get 2 minus 5 minus 1 as x plus z, x plus y, x plus y plus z. Therefore, we have the three equations. X plus z equal to 2, x plus y is minus 5 and x plus y plus z equal to minus 1. Solving these three equations for the three unknowns x, y, z, we get z as 4, x is minus 2 and y is minus 3. Therefore, our T of V2 equal to 2 minus 5 minus 1 we have assumed as xv1 plus yv2 plus zv3. Substituting for x, y and z, we get T of V2 as minus 2V1 minus 3V2 plus 4V3. Therefore, T of V3 equal to minus 2V1 minus 3V2 plus 4V3. These scalars minus 2, minus 3, 4. This gives our second row of M of T. Now T of V3 equal to, substituting for V3, it is T of 1, 0, 1. Using the definition of T, we get T of V3 as 2, minus 5, 1. So as before, let x, y, z be the scalars such that 2, minus 5, 1 is written as a linear combination of V1, V2, V3 as xV1 plus yV2 plus zV3. Substituting for V1, V2, V3, we get, and after simplifications, we get 2, minus 5, 1 as x plus z, x plus y and x plus y plus z. Therefore, we have the three equations as x plus z equal to 2, x plus y is minus 5 and x plus y plus z equal to 1. Solving these three equations for x, y, z, we get z as 6, x is minus 4 and y is minus 1. Therefore, our T of V3 is minus 4V1 minus V2 plus 6V3. Let this be equation C. So, from equations A, B, C, we get M of T. Matrix of T as minus 4, minus 2, 7 from equation A, minus 2, minus 3, minus 4, second row from equation B, and from third equation C, we get minus 4, minus 1, plus 6 as the third row of M of T. So this is matrix of T belongs to A of T. So this is how we find matrix of a linear transformation. Proceeding to the next problem. If the matrix of a linear transformation T on R2 with respect to the first basis V1, V2 is 1, 1, 1, 1. Find the matrix of T with respect to the basis W1 and W2. So here only we are applying the theorem which we learnt in this video. So M1 of T is given. Our purpose is to find M2 of T. So we are going to use M2 of T equal to C M1 of T C inverse, where C is M1 of S and S is invertible. So we are going to apply the theorem on matrix of change of basis. Coming to the solution, the matrix of T relative to the first basis is given as M1 of T is 1, 1, 1, 1. Let M2 of T be the matrix of T relative to the second basis. Let S be the linear transformation on V defined by VIS equal to WI for I is equal to 1, 2. Here we have only two vectors. Then V1S is equal to W1. Substituting for W1, it is 1, 1. It can be written as 1 into 1, 0 plus 1 into 0, 1. 1, 0 is V1, 0, 1 is V2. So we get V1S is equal to 1V1 plus 1V2. We get a linear combination of V1 and V2. Similarly, V2S is equal to W2. Substituting for W2, we get it is 1, minus 1. It is written as 1 into 1, 0 minus 1 into 0, 1. That is nothing but 1V1 minus 1V2. So V2S is written as a linear combination of V1 and V2. Therefore, the matrix of S relative to the first basis is 1, 1. And scalar from the equation V2S is 1 and minus 1. So we get the second row as 1, minus 1. Therefore, matrix of S relative to the first basis is M1 of S is 1, 1, 1 minus 1. Let us take C as M1 of S. Now our purpose is to find C inverse. So we use the formula C inverse is HC by determinant C. So determinant C is minus 2, which is non-zero. So we know C inverse exists. And finding the cofactor matrix, adjoint matrix C. Therefore C inverse is nothing but 1 by minus 2 into minus 1, minus 1, minus 1, 1. So this is C inverse. So applying the formula, M2 of T equal to C M1 of T, C inverse. Substitute for C, M1 of T, C inverse, and we get C2 as, after the necessary computations, we get M2 of T as minus 1 by 2 into minus 4, 0, 0, 0. Therefore, M2 of t is nothing but 2, 0, 0, 0. So, given M1 of t, applying the theorem for matrix of change of basis, we can find M2 of t, that is matrix of t relative to the second basis. So, this is the application of the theorem. Thank you, friends.